Hey, so this is Joe, and this is the first video for the 11th chapter, the 11th and final chapter, in terms of single variable calculus, of Stewart's calculus. And we're going to be talking about sequences today. So a sequence is kind of like a function in that it is a set of numbers that depends on another set of numbers. However, instead of the set of numbers upon which a sequence depends being all real numbers like x, like for a function, this set of numbers is just increasing integers. So what does a sequence look like? How do we write it out? Well, say we have a sequence A. We describe it generally as some sequence. We can describe it with the variable n over n plus 1. This is just one kind of sequence, and it will go from n equals 1, and this will be an infinite sequence, so it'll go all the way up to infinity. And so this means that if we were to write out this sequence entirely in terms of each term, because this is just the general expression, we would write it out as, okay, so we plug in n starts at 1, we plug in 1 for n, we'd get 1 over 2, and that's the first. And let me write out what n is. So when n's 1, the sequence, the term of the sequence, the first term is a half. Then we raise n by one integer, and there's unlike a function, you don't have a bunch of little points between n equals 1 and n equals 2. They're just these two values because sequences only depend on incrementing integers. So we put in a 2 for n, we'll get 2/3, and so that's when n's 2. Sorry. When n is 3, we'd get 3/4, and so that's when n's 3, and then when n's 4, we'd get 4/5, and so on until we get to a of n, which would be so this is the first term, second term, third term, fourth term, and it's reflected by the n values up here, and then we'd get to the a of nth term, and generally that's just we write back out what the sequence is, and so on. So all a sequence really is a set of numbers described like this, and unless otherwise specified, the range of a sequence is always going to be between n equals 1 and then infinity, because generally sequences are interesting when we deal with infinite sequences, so ones that go up to infinity, and it's just a convention that mathematicians use. Generally we like to start at 1. That's just kind of a general rule. So that's what a sequence is, but does a sequence, when we have an infinite sequence like this, does it ever stop? Can it ever stop? Is there ever going to be one value that we'll get and then that's the end? Well, let's see, because that's where sequences get a little bit interesting. So we can also ask when if a sequence ever ends, that means that it would converge. That means there would be one value that the infinite sequence would end up at, and it wouldn't go past there no matter how large the value of n becomes. And this term convergent, we've used this before when we're talking about improper integrals. And if you remember an improper integral, when the integral converged, the curve gets really close to the x-axis, and the area underneath it becomes definite. Well, there's a similar sort of graphical interpretation that we can use with sequences. So let's get back the sequence that we were dealing with on the previous slide. So we got the sequence described by n over n plus 1 between 1 and infinity, and we've got all of our values of a of n right here, and we've got all of our values of n. Well, what if we plot this out as a curve where we have our x-axis, we call that n, and our y-axis, we call that a of n. So n, we get, when n is 1, we'd get a half, and then we'd get 2/3 when n is 2, and then we'd get 3/4 when n is 3, and we get 4/5 when n is 4, and we can't really draw a line connecting these points because it's not a function. That there aren't points in between those values, but if we can imagine this curve kind of going on, we could say, well, maybe there's a certain line that it approaches and never goes past, and there's a certain line that it gets so close to that basically it ends up just reaching that value once we get a super big value of n. And so that doesn't mean that this is a sequence that necessarily converges, but we can kind of think about that and say, well, there might be other sequences at least out there that would converge to a single value. And in fact, there are, and I'm going to basically tell you right now how you can identify those. So if we have a sequence A of n, so any sequence, we can figure out if it converges if we take the limit as n approaches infinity, and so this is presumably an infinite sequence. And if we take the limit as n approaches infinity of A of n, and if that equals some L, where this L is both real and so actually really if it's just a real number, if this limit exists and is real, then that means that that sequence converges to that value. So that's basically where the sequence will end, no matter how big the n value gets. And so let's try it out with the sequence we were using before. Let's try it out with A of n equals n plus 1 between 1 and infinity. Let's see if this converges. And remember, it kind of looked like it may, because it was making a movement sort of like this, almost looking like a logistic growth curve. And we know that a logistic growth curve converges, the values all kind of approach the carrying capacity. And so that it looked like it was kind of moving in the same way, but let's use the sequence convergence theorem with the limits and figure that out. So we'll take the limit as n approaches infinity of n over n plus 1, and we can apply L'Hopital's rule, because when we plug in infinity into the numerator and denominator, we get an infinity over infinity, and so that equals the limit as n approaches infinity. Take the derivative of the top, that's 1, take the derivative of the bottom, that's also 1, and so that limit is 1. 1's a real number, so that means that this sequence converges at 1. And that's a pretty not too complicated of a concept, and let's just I'm just going to tell you two other concepts about sequence convergence that will be helpful for later on. And I'm not going to prove them right here, although your book does a good job. You just kind of need to know these properties. Alright, so here's some of our sequence convergence rules and definitions. So number 1 is the one that I just told you. It's the most important one, best test for convergence or divergence. So if the limit of a sequence is a real number, it converges, and if the limit of a sequence either doesn't exist or is plus or minus infinity, then it diverges. We just went over that. So number 2, so there's some sequences that are alternating, that'll have alternating or just always negative. So you may have something like this where you have a negative 1 to the n, and that's your A of n. That's not always positive. So it sometimes is a little tricky to take the limit of it, but what you can do is if you take the limit of this sequence as n approaches infinity of the absolute value, so basically just get rid of that negative, and if that is equal to 0, then the sequence with the negative, the alternating sequence, is also converges at 0. So that's kind of a handy one, and it's one that you should bear in mind if ever you have a sequence with a negative or an alternating sequence like this. So number 3, so the limit as n approaches infinity of r to the n, so any number, any constant to the n, will converge at 0 if r is between negative 1 and 1. So if it's like a half or a negative third or a fourth or something, it'll converge at 0, and it'll converge at 1 if r is 1. So I just also want to remind you for this property especially, on the AP, if this is on a free response question, you wouldn't be able to use this this isn't a property that you can cite as proof for convergence. You would actually have to still do the limit test on this. You'd actually have to solve this limit. You wouldn't just be able to write down that this limit is equal to either 0 or 1. But on the multiple choice section, definitely this is very helpful to remember because it saves you a lot of time. Alright, so moving on Number 4, this is a definitional one. So if a sequence, we call it increasing. If a of n plus 1, so the term in front of the term you're on is greater than the term you're on. So if you have one term and the next one is always bigger, you call that sequence increasing. And decreasing, if for every term the next term after is always smaller, gets smaller and smaller, you call that decreasing. That kind of makes sense. And I'm going to skip down to number 6. And a sequence is called monotonic if the sequence is not always increasing or decreasing. So if it's like cosine n, that's your sequence, that's going to be monotonic because that goes up and down, up and down. It's a cyclical function, right? And that's helpful for the 7th property, but I'm going to talk about the 5th one first. So you call a sequence bounded by above, if the sequence is always less than some value m. So that's kind of, you can call the sequence that we were looking at n over n plus 1, that's bounded above by some m because it's always approaching this value. When we kind of graphed it out, it looked like it was approaching a certain value, kind of like a logistic function or like a function with an horizontal asymptote. That's what bounded above is for a sequence, and bounded below is if the sequence is always greater than m. So kind of like exponential decay, when it approaches the x-axis is kind of asymptotic with the x-axis. If you were to graph out a sequence, it would kind of look that. So a sequence is bounded below if the sequence is always greater than a certain value, one value. So number 7, we come to an actually pretty important property right here. If you have a series, a sequence that's both bounded either above or below and monotonic, that sequence always converges. So if you have like a multiple choice question, and it gives you a sequence, and you identify, and all you need to answer is whether or not it converges or diverges. If you see that it's bounded and monotonic, don't go any further, don't do any limit work, just write down that it converges if it's both bounded and monotonic. Now, if it's not bounded and not monotonic, that doesn't mean that the sequence is going to diverge. You do have to do your limit work for that. But that's pretty much all you need to know for sequences for this class. So now let's just do a couple practice problems and kind of start getting the hang of this. Alright, so we're going to do number 42 on page 724. And we're given the sequence, the natural log of n plus 1 minus the natural log of n, and we're asked to figure out whether it converges or diverges, and if it converges, figure out what it converges to. So this means we're probably going to need to do some of our limit work, since this is neither a sequence r to the n, and it's not a sequence with a negative in it. So we're going to have to do our limit work. So we're going to take the limit as n approaches infinity of a of n, which is going to equal, and remember our properties of logarithms, when we have a logarithm minus another logarithm, we can divide the exponents. So this will be, we'll just substitute that directly, the natural log of, and remember it's always the absolute value, n plus 1 over n. Now, we can't quite do L'Hopital's rule because this argument is inside of a natural log, and we could do some reorganizing, but that's not really necessary. There's a we don't really need to use L'Hopital's rule for this limit. So we can split up this fraction, and the n over n is going to become a 1 plus a 1 over n, and when we put our infinity in here, this 1 over n is going to approach 0 eventually. So we can actually just evaluate this limit right now. We're going to get the natural log of 1 plus 0, and that is equal to the natural log of 1. And if we remember that, the natural log of 1 is 0. So this limit, this sequence, converges at 0. Not too difficult. So let's go on to another slightly more difficult problem. And remember, all these problems with sequences, because you evaluate them using limits, really the hardest part about them is the limit. If it's a tough limit to solve, it's going to be a tough problem to solve. But so yeah, we're just going to get some good limit practice here. So now we're going to do number 50 on page 724 in your book, and the sequence is the natural log of n squared, not the argument squared. If we had the argument squared, this would be a much easier limit to solve, because when you have an exponent in the argument of a natural logarithm, you can bring that exponent out to a coefficient. That's not the case this time. The whole natural logarithm is squared. So when we take this limit, which we're going to need to do to figure out whether this sequence converges or diverges, this is going to be a little trickier to solve. We're going to need to do some L'Hopital's rule. So let's get right to it. The limit as n approaches, in order to figure out whether or not this converges or diverges, we're going to need to take the limit of the sequence and figure out if we get a real number. So we're going to take the limit of the natural log of n squared over n, and when we plug in infinity here, the natural log squared becomes an infinity, this becomes an infinity, so we have one of our indeterminate forms, so that means we get to use L'Hopital's rule and take the derivative of the numerator and then the derivative of the denominator. So because of the chain rule, we're going to have to take the derivative of all this and then the derivative of what's inside. So we're going to get 2 times the natural log of n times, what's the derivative of natural log of n? It's going to be 1 over n, and the derivative of n is going to be 1. So we can rewrite this limit as 2 times the natural log of n over n. And this still gives us an indeterminate form. This still gives us infinity over infinity when we plug in an infinity for n. So we're going to need to do L'Hopital's rule a second time. So this is much easier to solve. We're going to get 2 times 1 over n, the derivative of the natural log of n is 1 over n, and then the derivative of n is just 1. So we got 2 over n here. The limit as n approaches infinity of 2 over n. When we put that infinity for the n, that fraction becomes a 0. So this is a 0. And so once again, like the last problem, this sequence converges at 0. So that was a little tougher to solve. We had to do L'Hopital's rule twice, but really it just comes, convergence of a sequence really just comes down to how well you can solve limits. So if anything, this is just good practice for the AP for solving limits. So let's go on to the last and hardest problem, because this problem we're actually going to need to use in a more involved way some of the properties of sequences that I was mentioning a couple slides ago. Alright, so now we're going to do number 43, and our sequence a sub n is cosine squared n over 2n. So before we go to solve this limit, we need to kind of analyze this sequence a little bit. So first off, this is the first one we're using a trig function for, and we know that cosine exists only between 1 and -1 inclusive. So that means that this, because cosine squared of n only exists between 1 and 0. So, and it goes back and forth between them as n gets bigger and smaller. So that means that this sequence is monotonic, because it's not strictly increasing or decreasing. And remember that the last kind of rule that I gave you on that slide said that if a function is a sequence is both monotonic and bounded, it's always convergent. Well, so we've already got halfway there. It's monotonic. Why not see if it's bounded? That'll save us a lot of trouble. Alright, so what we have to do then is prove that this is always greater than a certain number. So n starts at 1, right? And it keeps getting bigger. Well, as this n gets really, really large, this starts approaching infinity and everything starts approaching a 0. But there's no way that this function can ever get under 0, right? Because cosine squared right here will never be negative. And this will never be negative because it can't. There's no way you can pull out a negative of this from an exponent, since the exponent's the only thing that's changing. So we can say that a of n is always greater than 0, and therefore, these 3 little dots mean therefore, it's also bounded. So, because it's monotonic and bounded, we can say that this sequence is convergent. And so that's a good, quick little analysis to do on a multiple choice question, but this question also asks us to find where it converges to. So we're going to need to do the limit talk anyway, but that's just some interesting that's worth noting for this function. Because it kind of makes some of the work a little easier, and we can rely on the fact that if we don't get a limit that exists, we've done something wrong, right? So we'll take the limit of cosine squared of n, or 2 to the n, and this limit's super easy to solve because this cosine squared n is always going to be a constant, right? When we plug infinity in there, it's just going to be, this value is going to be somewhere between 0 and 1. When you plug infinity into the denominator, this is going to turn into an infinity. So what we've got is we've got a constant over infinity. And if we have 1 over infinity or 2 over infinity, that's 0. Well, that's the same with any other constant. So that means that this limit is going to be equal to 0, and it's going to converge at 0. So that's it for sequences. Stay tuned for this last chapter of Calculus BC. We're going to be going on to infinite series later, which are super interesting. We're going to be going on to Taylor polynomials, Maclaurin polynomials, Lagrange error, all very exciting stuff. This is kind of the most difficult part of calculus, where everything converges. Well, not really. It would make everything a lot more difficult. There are going to be things that will diverge, unfortunately, but definitely stay tuned for this. This is a very exciting chapter. Thanks.